everyone. We're getting a ways through our shortcuts list, and in this section we're going to tackle what's probably one of the most important shortcuts, and that is the chain rule. So we've built up a pretty good list of shortcuts for specific functions. We've got all the power functions, the exponential functions, the trig functions. We have a few more to add, but not a ton. We've also built up some shortcuts for combinations of functions. So we know what to do if we're adding or subtracting functions. We know what to do if we're multiplying or dividing functions. But one of the really big operations that we do with functions is not on this list yet, and that is composition. So what do we do when we've plugged one of our basic functions into another and we want to find the derivative? So this whole lesson is going to be working towards how do we do that. And I've really worked to build it in kind of an inquiry-based way where I want you to really look at some derivatives and investigate and try and recognize the pattern and discover what this shortcut's going to look like for yourself. I could absolutely just give it to you and start doing examples, but for the chain rule, I really want you to think about what's going on with these. So what we're going to do is we're going to go through 3 different steps of this, and you have a whole list, so we're looking at it right now, of derivatives that have already been calculated for you. And I want you to look through original function and derivative and see if you can figure out what the pattern is. And then there's 3 spots at the bottom for you to make a guess as to what the next derivative is going to be. So please look through, make those guesses before you continue, and then I'm going to work through all of this and tell you what I hope you spotted and tell you what the derivatives are. Starting back at the top, I'm going to zoom out just a little so we can see all of them. When I look at all of these, if I'm looking at the original function, one thing I notice is that every one of them has this 5th power. So all of them are some function raised to the 5th power. The function that I'm raising to that power is changing every single time and getting a little messier as I go for the most part. So that is what's different in all of these. So basically, outer function is x to the 5th, raising to the 5th power, and inner function is changing. What I notice on the other side is that I always have this 5 out in front. I also notice that they all have this 4th power, and I'm guessing that you are probably pretty able to guess where that's coming from or see where that's coming from. Since our original function has that 5th power as the outer function, the derivative should have a 5 blank to the 4th going on, because that's how we take the derivative of something to the 5th power. The other thing that I hope you spotted, that's maybe a little trickier, but I bet a lot of you did spot it, is that the function in here, x, its derivative is 1. And maybe this first one looked weird to you at first, because why in the heck am I writing that 1? We already know that the derivative of x to the 5th is 5x to the 4th. But as you went through, hopefully you spotted why that fits the pattern. The second function, 2x, is the inner function. Its derivative is 2. X squared, its derivative is 2x, and that continues down. Some of them get a little messier. This one requires a product rule, so what you're seeing out here is that product rule to take the derivative of the inner function. The bottom one, for now I would say we need a quotient rule, although there will be other ways to tackle that once we've established the chain rule. So this is the result of the quotient rule happening. So if you're seeing all that and we want to continue the pattern, I look at this and I say, okay, I have inner function raised to the 5th power. So my pattern tells me that I should do 5 times the inner function, exactly as it originally appeared, raised to the 4th. And then in the parentheses, I should have the derivative of the inner function. So the inner function is a sum. I'll look at piece number 1 first, 7x to the 8. If I drop the 8 out in front, I get 7 times 8, which is 56. And then the new power is 7, 1 less than the old power. Then I have plus 6x to the negative 3. So again, a power rule, so I need my plus. The power drops down. 6 times negative 3 is negative 18, so actually I want a minus. And then it's x to the negative 4. I need negative 3 minus 1. So that's what you should get for that first one if you spotted the pattern correctly. For the next one, again, drop the 5 down, leave the inner function alone, and then multiply by the derivative of the inner function. E to the x over x to the 4th, we're going to need the bottom times the derivative of the top minus the top times the derivative of the bottom, which is 4x cubed. And then that should all be over the bottom squared. X to the 4th squared is x to the 8. So something like this. And then last one is just asking you to generalize. So we've looked at all these examples of functions raised to the 5th power, and we've looked at their derivative, and hopefully you can generalize the pattern. You need to apply the power rule to the 5th power, drop the 5 down in front, leave the inner function alone, the new power is 4, and then you need to multiply by the derivative of the inner function. So that is example number 1.